Okay, welcome to the first vodcast on cosmology. We're going to look in this introduction at what cosmology is and some early cosmologies. There's no actual specific parts of the topic IB course we're going to look at here, but I do feel that you really need this brief introduction. So by cosmology is a branch of physics or astrophysics, but it's a bit different and it goes a little bit beyond. And its content is you could argue its content is everything, but certainly the content is the science of the origin and development of the universe. And I would also add to that specifically the ultimate fate of the universe. What will happen to the universe in the far future? And the important point is, and the important point we have to consider, of course, with all of physics, but particularly with cosmology, in that any model of the universe must explain all of the observed data. If it can't explain any of the observed data, or any single item of observed data, it is not a complete or adequate explanation. Sometimes you have a variety of models which can explain the data, and you have to choose between them based on how best they fit the data and how they tie in with the rest of our knowledge about physics. When we do talk about cosmology, we are talking about scientific cosmologies. There are, of course, religious cosmologies or fictional cosmologies, but we're interested in ones that don't appeal to faith or other aspects that are not so scientific. And we'll really start with the whole idea of crystal spheres. Crystal spheres unified cosmologies from the Greeks to Copernicus and beyond. And it was this idea that you had in the Greek, well, most of the Greek versions, the Earth at the center, and things were arranged at different distances from the Earth. So the Earth, then the Moon, then Mercury, then Venus, then the Sun, then Mars, then Jupiter, then Saturn, which was all of the classically known planets. And then you had the stars beyond, which maybe were on the inside of a dome, and maybe there were holes pierced, and there was a huge big fire behind the holes, or something like that. People like Ptolemy were able to explain the motions of the planets by looking at epicycles and other such things that you can investigate if you're interested. Copernicus comes along, and in 1543, he develops a Copernican model. In many ways, the Copernican model was not a huge new advance. Some people, back to the Greeks, already had sun-centered cosmologies. And he still came with the idea of whole crystal spheres thing. All he did, and it wasn't a small thing, but all he did was to swap the place of the Earth and the place of the Sun, and help develop what we now call the Copernican principle, which basically is that we are nothing special. I'm not sure Copernicus himself would have exactly said it like that. Giada Bruno is another interesting character. He was born in 1548, so he's kind of the next generation after Copernicus. And in this rather scary Assassin's Creed looking statue here, he was quite revolutionary in that for the first time in his cosmology, the universe was this infinite thing with no center, and the stars, his insight was that the stars, he thought, were suns like our own, just very, very far away, and that they could have planets around them, and those planets could have intelligent life, etc., etc., etc. This was a rather hierarchical view. No, not hierarchical view. He rejected hierarchical universes. This was an heretical view, and for this he was unfortunately burnt at the stake in the year 1600. Cosmology can be dangerous. Isaac Newton. Now, this continues the interplay of science and religion on this aspect. Isaac Newton was many things, but he was amongst those things also a deist. He did believe in a deity, and he wrote this series of letters to Dr. Bentley, who was a bishop, I believe, some arguments in proof of a deity, and it's quite an interesting. And if you pause and read the text here, you'll see kind of his argument or his primary argument. To summarize, though, Isaac Newton obviously developed his theory of gravity, and he believed the universe to be infinite and therefore centerless and edgeless. But he realized that his theory predicted that a static universe was either impossible or at best very, very unstable, and that if you had any areas that had a greater density um, of his universe, then by his calculations, they would all fall and make one, big mass. Um, his solution was that the fixed stars are equally spread out, precisely equally spread out, cancelling all of their gravitational attractions. This was his argument for a deity, because he argued that such a thing was impossible, and therefore you needed a god to keep everything in place. So that was the first problem with Newton's conception of the universe. It has no center, no edge, it's infinite, and it must be extremely homogeneous. And the gravity is the first problem to that. It's just not gravitationally stable. The second problem with a universe as pictured by Newton and his contemporaries was first, well, it wasn't actually first described by Mr. Olbers. It was actually, he wasn't the first person by any means, but his name has become attached to this, which is Olbers Paradox, which he published in 1823, so a good 150 or so years after Newton. And he pointed out, as others had, that if every line of sight, if everywhere you look ends on a star, which it must do by definition in an infinite and homogeneous universe, then the sky would appear to be the same brightness as the stars. Mathematically, you can consider this if you think about a shell with a certain thickness. Then there'll be a number of stars within that shell, all of which will give you a total output. If you make the shell bigger, then you're further away from those stars, so the output from each star as received on Earth, the brightness will be less, but there'll be more stars in the shell. And actually the two, because of the inverse square law, the two things cancel. So for any shell of given brightness and given density of stars will give off a certain flux, and it doesn't matter how far away that shell is, because it's bigger, further away but bigger. And if you have an infinite number of shells, which you have to have in an infinite universe, then the sky would be infinitely bright, which of course is impossible. His basic argument is illustrated quite nicely by this little animation. So we have lots of stars and then further away stars, but basically they do fill in all of the gaps, because even the furthest away star is not really a point object. It does occupy a diameter, even if it's a very, very small one. Okay? Thank you very, very much.